This is a lesson on audible qualities of sound in the simple harmonic motion and waves unit. In a previous lesson, I had looked at the properties of sound. Sound is a disturbance of matter created by a vibrating object, and we can see that the speed of sound is different in different mediums because of the dependence on the medium. It's a longitudinal wave where the vibration of the particles happen back and forth in response to a pressure. It's a pressure wave. And so we see that there's a compressed region and a rarefied region when we look at the wavelength of a sound wave. The speed of sound is the same for all waves, which we know is f times lambda, or lambda f. And there's a picture. Notice that it radiates outward in all directions, so we will use any qualities for spheres when and if we need them. So when we think about sound and hearing and the audible qualities of sound, there are a few different ones that come to mind that are important, and I'll quantify a few of them, but I won't quantify many of them. The first that I will quantify is loudness or intensity, and this has to do with how much energy is coming at you and related to the decibels scale. Pitch and notes is related to frequency, how fast that wave oscillates. So that's the frequency of sound. When we look at wavelength of sound, we can see that, of course, there will be interference of waves, sound waves, like any other wave, and that relates to harmonics, like how do multiple wavelengths interfere with one another. And this brings about musical instruments. How do musical instruments work? The last quality is called quality or timbre, where you have multiple different wavelengths from different objects lining up with one another, and we get an overlay of harmonics. Hearing, of course, has its limits on loudness and frequency. When I think about human hearing, it can be too soft or too loud to hear. And also the frequency, different animals have biologically different ear structures that allows them to hear different frequencies that human beings can't hear. So dogs, elephants have different frequencies that they can hear. Loudness or intensity refers to the energy in the sound wave, and we had talked about wave energy with intensity before. We know that intensity is power over area, and notice that this P is a power here. And the density of power that passes perpendicularly through a surface area. That's why I included this picture over here where I have the 5 sound waves and they go through 2 different areas, and the intensities are different because the area that that energy is dispersed over is larger in the second case. What I will tell you about sound waves is that the sound waves depend on the amplitude of the pressure. And I've not talked about this previously, that the energy of a sound depends on the amplitude. So energy depends on actually the amplitude squared. And I'm going to say, though, however, we're not surprised about this because the potential energy, elastic spring potential energy, is 1/2 K delta x squared, so that would be the amplitude squared. So we're not surprised to see that the amplitude is in here. So the intensity of sound, and you can see the amplitude over here. I have a regular bird and the angry bird is here from OpenStax. The angry bird here is louder, and you can see that the pressure, rarefications, and compressions go farther apart. They have a larger amplitude than the regular bird, the smaller amplitude. So when I look at the equation, there's the pressure squared, delta P squared, which we will define to be from here to there. There's 2, the volume, mass, density, rho of the material. So in this situation, it would be air. And then finally, V is the speed of the wave, which we know how to find is lambda F. So that's how you find the intensity of sound. It depends on this pressure difference. When we think of intensity, instead we think more of maybe decibels, not how much does that pressure oscillate, but how loud do we perceive it to be. And so intensity of sound, when you measure it in decibels, is a sound relative to the threshold intensity to hearing. So there's a low intensity, the minimum intensity that humans on average need to be able to have energy-wise in order for it to register in our brain as a signal. And we call that the threshold intensity. You can see that down here. It's called I naught. The threshold hearing level for human normal hearing It's 1 times 10 to the negative 12th watts per meter squared, which is super small, right? Super, super small, 10 to the negative 12th. Remember, we have a small area for our eardrum. That's a tiny one. So it doesn't take a lot of energy to hit that area to begin with. But also, our hearing is so sensitive. The hearing that we, speak with, or hear speaking with, hear music with, hear noises with, are carried through air. They're carried through air to our ears. So it's very sensitive to motion of air molecules. So that's a pretty sensitive intensity, to be honest, that it's very, very small. It's not as small as other animals, but that's what it is for the human ear. So in order to find a measurement in decibels, we take 10 times the log of the measured intensity over this threshold intensity. And what I'm going to tell you, 10 is just a number. It's the factor of 10. Log is a math transformation, and it makes exponential growth factor look linear. So there's some exponential growth going on, and that's how this is made a number in reference to our lower value. Using this equation, you will need to use the log button on your calculator. If you're not familiar with that, get familiar with the calculator. There's a log button. And we're going to assume that this is a log base 10 as opposed to a log base 2 or a log base E or any other log. So when we run that through the calculator and get it out, we will get a beta value. This is Greek letter beta. And it is measured in decibels. That's the units. There's no special reason why this is in parentheses afterwards, other than your book wanted you to know that this beta is in decimals. That's the units of this number. So that's decibels. The decibel scale, what are we looking at here, right? You're familiar maybe with the measurements of decibels, but to get familiar with this, it's like a temperature for your ears. What is hot and what is cold, right? And I grabbed a scale from 2 different sources here. And when we look at the one on the right, I like it because it does kind of say like these decibels are okay for our ear in general, but when you start getting into these regions, especially up here, that's will cause hearing damage. Down here, the threshold of hearing, all we hear is noise or nothing. So in terms of energy, this is higher energy, right? Down here is lower energy. We cannot stand very much energy all at once. So there's a threshold of pain. And in this region, when we get that much energy all at once, we get a lot of energy all at once will cause damage, which is why it's all in the red and orange and yellow here. In here with the yellow, and you can see the different types of examples of situations of noise that correspond to these values. In the yellow, you can stand it for a small amount of time, but for a long amount of time or many days in a row, etc., if you have an extended time, it will damage your ear. And so different headphones, noise eliminating headphones, are designed to eliminate these different types of sounds. So let's look at situations. A jet engine up here, we can see a jet taking off, or a jet engine is around 130, which is pretty loud. Those people out on the airfield use headphones. We might have a rock concert or heavy equipment that go by. Car horns are pretty loud. A nightclub with music. If you are in that, you will have hearing damage over a long time. We know that with rock concerts as well. Blow dryers, construction sites, motorcycles, lawnmowers, boiler rooms, if you're ever around a boiler room anymore. Fancy restaurant, maybe, where it's just like this loud din in the back, a freight train, classroom chatter, as opposed to the smaller things, a silent study room, a watch ticking. You might be familiar with the noise of a watch ticking. A whisper is down here, about 30 decibels. And so you can see that the energy, and we can do this with our voices, right? We can put not a lot of energy into it, or we can put a lot of energy into it, and we get that whole scale, right? So let's look at a couple of examples here more specifically. Here I have the sound level of an engine, and I put the equations up here with this threshold level of intensity for us to use. A woman stands a distance d from a loud engine that emits sound uniformly in all directions. We were already assuming this, but they've confirmed it. The sound intensity at her position is an uncomfortable 0.0032 watts per meter. What is the sound level at her position? So I wanted to put this terminology in here. Sound level will typically refer to decibels. If they want the intensity, they will say intensity specifically, and that will be units of watts per meter squared. If they want sound level, that's decibels, and you'll have to run it through this equation here where you get the decibels out. So let's do that real quick for part A. The beta value at this first position is going to be 10 times the log of the intensity there, which we know is 0.0032, and we divide by I naught, and I naught is 1 times 10 to the negative 12. So you'll get used to the exponential system on your calculator, and when you run this through your calculator, beta 1, I get to be 95 decibels. And I expect that from an engine. It's pretty loud. Like I said, people wear ear covering, ear protection near them. So 95 decibels. Not terrible, but definitely not something you want to stand around next to all day. The next question pertains to a different situation at a position twice as far from the engine. So I'll put D2 is twice times D1. They had a D up here, so that's why I'm using D's down here. It may be more appropriate, since sound radiates radially, to say that R2 equals twice R1. And then that way we can have the spherical nature of sound taken into account. It says, what are the sound intensity and the sound intensity level relative to the threshold hearing? So that's the same to me as the sound level. So let's find the intensity first. I know intensity equals power over area. And if I want to find intensity 2, that will be P2 over area 2. If I want to find intensity 1, that'll be P1 over area 1. And I'm doing a ratio here just because it's easier to think about the power. And you could do a substitution. You could write two separate equations and do a substitution, but sometimes it's just as easy to do a ratio and have things cancel. What I'm going to note in this step is that it's the same engine. So power 1 has to equal power 2, right? It's the same power that's radiating outward from the center. It's the same power, but it's over different areas. So P1 will equal P2, and you will see that this cancels on the top and bottom. And when I simplify this equation, I2 over I1 equals, well, I get 1 over A2 over 1 over A1, and that it simplifies to A1 over A2. I want to solve for I2. So let me do this first. A2 over A1. Well, the area of a sphere, right? We're dealing with spheres, a sphere here. The surface area of a sphere is surface area sphere 4 pi r squared. So I'm going to do a ratio here of 4 pi r1 squared over 4 pi r2 squared. And you may see where this is going. They never gave us this distance d anywhere in the problem. We could calculate it in theory because we have the intensity, we could calculate it. But I wasn't given it. The nice thing about this problem, notice that the 4 pi's cancel in the top and bottom, and I have the ratio of R1 over R2 quantity squared, or R1 squared over R2 squared, however you like to think about that. But R2 is 2R1, so I'm going to do R1 over 2R1 quantity squared, and you can see that the R1 cancels, and I wasn't given that value anyway, so that's perfectly fine. And I see when I simplify this equation, I2 is a fourth I1, right? A half squared is a fourth, and then if I do a step of algebra to bring the I1 over, I get a fourth I1. I1 is 0.0032, so I'm taking a fourth of that, and that will equal 0.0008 watts per meter squared. And that's that second intensity. Note that it's not just a factor of 2. We have some radial stuff going on with the sphere, and that will increase our powers. Now that I have this, I can find the intensity there, beta 2, at this second position will again be 10 log. This was I1, this will be I2. So I'm going to go 0.0008 divided by that threshold frequency, 1 times 10 to the negative 12th. And when I run this through the calculator, notice that I'm not going to get a factor of 2 on this 95 decibel. It doesn't go just a factor of half that way or a fourth or anything. When I run this through the calculator, I do this transformation on these numbers. Remember, it makes an exponential a linear value. And so I actually get 89 decibels, which is still kind of loud. It's still kind of loud nearby. And it's not a factor of 2. So watch out for tricks and questions like that. And also that tells you the power of this log function. The next problem I've chosen deals with some algebra on how to find an intensity if you know the decibels, which requires some algebra around that log function. I've called it hearing damage. Hearing damage may occur when a person is exposed to a sound intensity level of 90 decibels for a period of 9 hours. So again, if we get a lot of energy all at once, that will cause damage, and also if we get a lot of energy over a long period of time, that will also cause damage to our biological tissues. It says one particular eardrum has an area of 2 times 10 to the negative 4th meters squared. How much sound energy is incident on this eardrum during this time? Okay, so I'm given the beta value, 90 decibels. Okay, so I can see that goes into here, and that would give me, if I solve, that would give me the intensity. I have an area. They're giving me an area, 2 times 10 to the negative 4th meters squared, and that relates to this intensity equation. They're asking for energy, and they've given me a time as well. Remember, 9 hours, and then I'm going to need to convert 1 hour is 3,600 seconds, and that would be some time. I'm not going to calculate it now. I'm just going to leave it like that and focus on solving for what I want to solve for. I'm going to remember that power is energy over time. So when I write that out, I equals E over T over A. And they ask for energy. What is the energy? So when I solve that equation, I do a little bit of algebra. If I multiply by A and T on both sides, I will get energy by itself on the other. Great. So I have area and I have time, but I have beta, not intensity. So I need to relate the intensity to that beta. When I solve, right, I'm going to have to solve for this intensity out of this equation. And how we do that, let me write this equation down. 10 log I over I naught. Beta is a known value, but I'm just going to leave it like that. In order to isolate I will divide by 10 on both sides. So I get beta over 10 equals log I over I naught. And I'm going to use the definition of log. The definition of log is the log of some base of a thing equals the result. Log base b of x equals y. What that means is b to the y power equals x. In this situation, our base is 10. So that means that 10 to the beta over 10 value, right? That's the y value in here on this side. I take the base to that thing. That has to equal I over I naught. And when I'm solving for I will get I naught times 10 beta over 10. So now I have an expression. Those are all numbers I know. I naught is the threshold intensity. Beta is 90. So I'm going to fill that into the equation as well. So I get times I naught 10 to the beta over 10, close parentheses. Let's plug in numbers. The area is 2 times 10 to the negative 4th. The time is 9 times 3,600. I'm going to let the calculator worry about that. I won't write it out. I have 1 times 10 to the negative 12th. That's the threshold intensity. And then I have 10 to the 90 divided by 10, which is 10 to the 9th. When I look at this, I'm going to simplify a little bit because I just have powers of 10 on the end, right? This is 10 to the ninth power times 10 to the negative 12th power. So overall, this becomes 10 to the negative third power. I have 10 to the negative third and 3600. In theory, I could just move this over 3 decimals and have 3.6. And then that's all I would need to plug into the calculator. 2 times 10 to the negative fourth times 9 times 3.6. And when I run this through, you may see it gets lost with all these powers of 10 that this energy is actually not very large in general compared to maybe what we eat and put in our stomach. We get 0.00648 joules. I'll call that 6.5 millijoules. So, small energy, but that's all the energy that our eardrum can take over that 9 hours. Again, and you may relate this to springs, right? If I deform a spring too much or too far or too often, the material may become damaged in some way. And that's what happens to our biological tissue. It just becomes damaged. And it depends on the type of damage, the extent of damage, if there's permanent hearing loss or if it's hearing loss that may return. So now that we know how energy relates to the properties of sound waves and the audible qualities, let's look at the other audible qualities. The next I mentioned was pitch, which is the frequency of sound. It's directly proportional to the frequency of sound. That's what pitch is. Rapid frequency produces high pitch or high notes. The human limitations on pitch, right? If it's too low of a frequency or too high of a frequency, we won't be able to hear it. So there's the range of frequency that humans typically have. If you've ever done a hearing test, you know that they go through all of these frequencies from very low to very high frequencies. And so there's a limit. For humans to be able to distinguish pitches, they need to differ by 0.3% or more. That's just an interesting fact for two notes, two different sounds to be distinguished. And we know that hearing degrades with age, so that goes into human limitations. When you get older, the ear, the biological tissue breaks down and you won't be able to hear as well. Musical notes are pitches of particular frequency. And I put the octaves over here. Middle C is given in the fourth octave here. 261.5 is usually what it is. And you can see that the notes are specific frequencies. These are all specific frequencies, and that's how notes work. They're different multiples or fractions of harmonics. So octaves are just multiples of that. So C is also represented by 130 and 65 and 32, right? There's octaves of that. And then within each octave, there are different notes within that octave. And the notes are related to one another with these fractions or proportions. Here's a couple of pictures I grabbed from the internet as well. This one's from Wikipedia. Here's a musician scale that is called even-tempered. That's the even-tempered scale. And what they do is they center it on A being 440 hertz. The scientific scale, they center it on C being 256 hertz. So you can see that there's two different scales here. And most often you will see this, the musician scale or the even-tempered scale, out in music. Notes, you can see the relationship here when I was talking about frequencies. C and the C octave above it is going to be multiples of one another. And then each of the notes in between are a fraction of that original frequency. And so we get these cycles that go around. This is called the circle of fifths. So that's how frequency relates to musical notes. I wanted to take a second to look at frequency here. A little bit closer with an oscilloscope reading of a sound wave. And you can see two different ones here. I took this from Hewitt Conceptual Physics, Volume 10. The oscilloscope reading is shown for two different musical notes. Thoroughly justify your answers for the following questions by describing features on the graph you use to determine the answer. So it's not just give an answer, but let's reason out loud about why that is the answer. So it says which shows the longer wavelength. The definition of wavelength is crest to crest or trough to trough. So when I look at this first wave, there's trough to trough. There's the wavelength of that first wave. And I will call this wave big A and wave big B. I know that's a risk because I have little a and little b over here, but I'm sure you can handle it. So lambda A is this long. There's not two troughs in here, but I could pick any 2 points that are the same. I could pick this lower peak here. That would be just as equivalent. I just want 2 identical parts of the wave. And we can see that these 2 are farther apart for lambda B. So the wavelength we can see for lambda B is going to be greater than lambda A. And how I did this was crest to crest distance. And that may be enough to justify that what I was looking at on the graph that corresponds to my answer. The next one shows what is the higher frequency. Okay, so I know that you want to say A because they're closer together. And I'm not saying you're wrong, but that may not be the right justification because this is a picture in time. This is one picture in time. If I just take one picture, there's no time passing. So it's like waves on a string. I just take a picture and it's there. It tells me nothing about time. They could be oscillating. That the first one could be just really slow, like a heartbeat, and the second one be moving really fast. I don't know. What I do know is that they're both sound waves. If they're both musical sounds, they both have the same speed, VA equals VB, right? 343 meters per second in air at 20 degrees Celsius. What I also know is that lambda A times the frequency A has to equal lambda B frequency B. I'm going to do some manipulation here of this equation. What I'm going to get is, let's do frequency A over frequency B. Well, that has to equal lambda B over lambda A. Okay, if you do some algebra there. And I know lambda B is greater than lambda A. Lambda B is greater than lambda A. Remember, that's my conclusion from part A. So this fraction right here is greater than 1. It has to be greater, right? So when I look at this, frequency A is going to be greater than frequency B. And that's how I can tell without looking at that graph of just one picture in time. This isn't 2 times. It has a shorter wavelength, so it must have a longer frequency, which shows the louder sound. Well, we want to compare the amplitude of A compared to the amplitude of B. And when I look at the amplitude, if it's the same scale, the amplitude, how far these waves go above and below equilibrium position, is definitely smaller on A. So amplitude A is going to be the bigger one. And for this, I looked at the amplitude. Okay, so that relates the energy or amplitude to the frequency and wavelength. There's one last thing that I want to talk about, and it actually segues into the next lesson after this one, which is the quality of sound, the superposition of many tones differing in frequency, which is referred to also as partials. When you play a musical instrument, notice that there's a clarinet down here and a piano down here. When you play a piano string, and I talked about this before with sound waves interfering, that when they line up and this oscillates back and forth like a guitar string, when it oscillates back and forth, the lowest frequency that can happen in between these is going to be when the wavelength is twice this length here. But what you're seeing also is this vibration. Each of these vibrations can have their own vibrations. And this is what we call the quality, these partials that happen. And notice that the partials for a piano are not the same as the partials for a clarinet, which is not the same as the partials for my voice or your voice. So this deals with standing waves and interference of standing waves trapped in this particular medium. which is the next lesson. Notice that we're going to get an effect of beat frequencies in here as well when we look at the harmonics, overtones, and partials of interfering sound waves.